Thanks very much. Thanks very much for inviting me, Kevin. It's been a pleasure. It's really nice to meet the faculty in the biostatistics department and to meet all of you. And definitely, as Kevin said, we sit a couple of floors above. So stop by and say hi next time you're drinking the coffee. It will be delightful. So we're a lot of us are on the sixth floor, so you have to go a little bit higher than you otherwise would. But yeah, so basically, I wanted to talk today about robust methods for meta-analysis of dose-response relationships, which has been a long-running project, a joint collaboration with IHM. Actually, what started the collaboration has been going on since 2018, 2019, and the first thing that started it was this need to come up with methods to estimate dose-response relationships, and then we actually took a break and got into other topics like remodeling with COVID forecasting. I'm probably pretty sure you guys are aware, and then all these other things. But then like some of this work came out in 2022 and then has been sort of continuing. So there's probably for a lot of you, you're probably interested in this material. So that would be a really nice way to kind of kick off a research topic that might be engaging to you guys. Let me make sure. So this is a large group. So Peng and I started working with Chris directly on this topic of basically understanding the strength of evidence for domains based on meta-analysis. Started the work with Ryan and Reed, who are staff members, and they're currently continuing to expand into other areas like categorical risks with Nora Gilbertson, who's a research scientist at IHME, and then Sinclair helped a lot along the way, developing documentations and a lot of different papers. And then Susan's a staff writer who spends a lot of time helping different teams at IHME to get all the results in a unified format and basically make sure that there's a lot of quality control involved in the communications front. There's a lot of people involved in doing a lot of the work. So I have some slides at the end that kind of mention the paper so you can see a full list of all the collaborators there. Great. So the brief outline is going to talk about meta-analysis of dose-response relationships. And there's some interesting technical challenges, particularly when we think about nonlinear or log nonlinear relative risk. So basically describe how we can access solutions to those challenges using techniques in optimization and other things. Then there's also challenges in terms of communication and decisions to create additional metrics to report. And I want to get a little bit into that. So like as the talk goes, we'll go from pure sort of technological innovations to things that interact with interpretation, probably be interesting. And then hopefully at the end, I'll have some time to just show you some examples from the Viz tool. We can poke around for areas that you might care about, whether it's diet or blood pressure or whatever else you might be excited about, figuring out, from the set that we have of, what people have written papers on so far. Okay, so just a little bit about the Institute for Health Metrics and Evaluation. The Institute was founded in 2007 by Chris Murray, Emanuela Gakadu, and Michael McIntyre. We are funded by many sources, primarily by the Gates Foundation. And the mandate, this is the banner from the IHME website, basically GBD, the mandate is to understand and provide quantitative research in health, to basically quantify health loss across places and over time, so that health systems can be improved and disparities eliminated. So IHME produces a lot of estimates, studies a lot of outcomes, produces the Global Burden of Disease Study, which has to quantify the burden of all diseases, basically, across all locations, national and subnational, for many years, at fine granularity by age group. So it sounds like a kind of like a classic statistics project, but it's actually much harder than that because a lot of the times we're talking with the already is a lot of missing data. So a lot of the times it's kind of an interpolation, extrapolation problem and many facets. It's quite difficult, very interesting, requires a lot of methodological innovation. One aspect of this is risk outcome pair analyses. What is the impact of exposures on outcomes? And then how much disease is attributable to risk factors? So there's about 400 or so pairs, maybe 470 risk outcome pairs that are part of the GBD study. And then a lot of these have already been now analyzed with this burden of proof methodology that I will describe. So hopefully that sets some context for kind of where this work sits. It's really nice. great thing about being able to work with IHME, some of the work has kind of broader impact on these estimates and on policy. And I forgot to mention at the beginning with Biostat, there's a lot of interactions through students. So both Marlena Bannock and Katie Paulson, who are getting their PhDs in biostat or IHME staff. So this would be nice to see more collaboration with students and faculty with biostat. It's really nice. This is not a comprehensive list of collaborations by any means, but just like two things that popped to mind because then Katie's on the call. Yeah. Okay. So the broad idea with meta-analysis is meta-analysis helps us to understand relationships between exposure and outcome and informs policy. Um, so we basically would like to gather all the evidence that has been conducted, following appropriate guidelines from randomized controlled trials, cohort studies, case control studies, and then take all those results that are typically reported in published literature and then aggregate the evidence in a rigorous way in order to estimate effect sizes. And when we have a continuous something like exposure to smoking and pack years or consumption of red meat, also estimate the dose-response relationship. That's the goal. So the results from meta-analyses inform dietary guidelines, tobacco regulation, environmental policy, clinical practice. Basically, a single study can be important, but before all of this action takes place, people typically want to aggregate kind of all the existing information. So when I was getting my master's here and I felt like I was a statistician, what I would often do is I would often take a single study and I would start reading its methods very, very carefully, try to figure out if I agreed with the methods or if I could see some flaw. And so one of kind of like the biggest eye openers for me here is that there's many studies, and no matter how well they do things, the results can often disagree with each other. And so getting the totality of that in order to inform our best understanding is kind of what meta-analysis are about. So typical questions are, how does smoking affect lung cancer risk writ large? Does red meat consumption increase heart disease? These are some less controversial and clearly established, some more controversial areas still. And then like, how can we compare strength of evidence across these different domains? So when we get to nonlinear dose-response relationships and these cross comparisons, there's quite a bit of challenges there to overcome. The challenges can divide them into technical difficulties, and technical difficulties is what, like, coming from an applied math background, it's easy to discuss and get into. That's more like a classic methods talk. So actually going to start with some of those to give you guys a flavor. So most analyses still assume log linear relationships for simplicity, but nonlinear analyses are important because a lot of the risks are attenuated at higher levels of exposure. So I will show you that. So dealing with nonlinear risk is important. So that's a technical issue to overcome. And then robustness to outliers is also important, particularly in the tack that we've taken. So developing methodology that are robust to outliers is an important technological innovation. And then finally, between study heterogeneity, especially with few studies, is hard to assess. So if there's two of us and we disagree a little bit, is there big disagreement or not? Could there be big disagreement? So sparsity in emerging fields is another challenge. But there's other challenges with interpretation and communication. So if you start doing studies in a particular topic and the study results contradict each other, there was like some of the examples I had that I don't have in the deck, like eggs. Like eggs are good for you, an egg a day keeps the doctor away. Eggs are bad for you, don't eat any eggs. And so then people see this vacillation. Every time there's a study comes out, it's front page of the New York Times, the public loses confidence. But while that's happening, the classic confidence interval shrinks a little bit, even though the studies can contradict each other. So that philosophically motivates additional measures that can be used to report and compare these domains to each other. So that's getting into how the interpretation, the technical areas interact. So we'll talk about that a little bit as well. So basically we'll discuss the methodology and hopefully some progress in both the technical and in the interpretation category. Okay, so that's a lot of introduction. Now we can get into the bread and butter of it. I wanted to make sure to put up some simple models for basically linear analysis, linear meta-analysis. So maybe we have the two simplest linear models that I can present. The first one on the left is dichotomous, whether exposure is binary, exposed versus not. And the second one is assuming log relative risk. So we assume that the relationship is linear in log space. So if you look at, let's just pick a side here. You look at the equation. So suppose we have a bunch of studies, and each study returns for us one estimate of the effect size for the log relative risk of exposed versus exposed. And then what we're trying to do is we're trying to basically estimate a weighted average of these to report as the final aggregated effect size. And then each study has a random effect, UI, and that random effect is a study random effect, and we don't know the variance, but we're going to try to figure it out. But each study does report with their estimate, they report a sample size based observation error. So if you trust the studies, basically, if you were to trust the studies completely, the variance for each study would just be their reported sigma squared I value. And then the margin likelihood problem would simplify to just computing, minimizing a weighted average. Here you take the scaling equal to 1. So you'd be minimizing a weighted average of the reported yi's weighted by their inverse reported variance estimates, if that makes sense. And that's what you will get. And then from that estimate, you can then compute the posterior variance. However, you don't completely trust them because maybe there might be additional variance that they're not reporting, somehow the non-sampling error, and you try to simultaneously estimate that gamma. So that's called the between study heterogeneity. There's wide literature on this. It's a very simplistic presentation, but hopefully get the idea across. So for me, it's like some of them might be really optimistic in how certain they are based on the sample size. And you're trying to get, in the simple case, trying to get an inflation factor so that maybe instead of one says, I'm super certain I'm going to really trust that one, you add gamma to all of them, and then you take like more of an equal variance distributed when you're computing that sample size. Does that make sense? And so the marginal likelihood here captures that. So you're simultaneously getting the beta, which is the overall log relative risk, and you're getting the gamma that you're going to add to everybody. And once you do that, that'll affect your posterior variance. Does that make sense? Have you given me, if you can raise your hand if you've seen linear meta-analysis models before? But you've probably seen like mixed effects models before. So this is like a basic mixed effects model, and the only special thing is that this study report observation error is given to you as an input instead of being like shared across studies and unknown. That's typically like a only differentiating factor from like a simpler repeated measurement model. Okay, and then something very similar happens to when we have a log relative risk. So if we assume everything is linear, the only thing that matters is the distance and the exposure between the alternative and the reference. And so all of these things are scaled by the gap between the alternative and reference exposure. So this random effect acts now as like a slope random effect rather than an intercept random effect. So it's scaled by a z, which is the gap between the alternative and reference exposure. But then in the end, you get a really simple solution. So like the bread and butter problem is pretty nice and interpretable, and it's pretty good. Okay, so moving forward though, most dose response relationships are nonlinear. So nonlinear, in particular, they're attenuated at high levels of exposure. So this is vegetable consumption and ischemic stroke. And I kind of like this one because, you know, it made me want to eat more vegetables because it really falls off. So these dots basically correspond to the observations from all of the studies that after we did a systematic review, we want to meta-analyze. So the dots that are provided here, this one, the same color, they're that color because they're coming from one study. So the study reported like 4 estimates for different quartiles of exposure. And then this particular line shows the kinds of data set, the kind of data points that we get. So the kinds of data points that we get is people tell us, okay, we compare people who eating, from 270 to 370 grams of vegetables per day. We're comparing those to people who eat from no vegetables to 150 vegetables per day, and we're getting a log relative risk. So that's the typical data that you get. And then you can see, like, even if you close your eyes to the curve, you can see there's attenuation in the benefits from eating vegetables. So if you're already eating 300 grams of vegetables a day, if you eat 400 grams of vegetables, that's kind of a marginal benefit based on the data. So when we're talking about nonlinear relative risk, Yardi is in the audience, so we can definitely use splines to capture the fact that the risk is nonlinear. We can model it with a spline that translates the shape, the nonlinear shape of the risk, as a linear combination of spline coefficients. But the difficulty is that the observations are actually these ratios of risk, aggregated risk, average risk between the alternate and reference exposure. So basically, that was a problem to solve because existing methods would make simplifying assumptions to limit accuracy, like midpoint approximations. Before we get there, though, I wanted to just say a little bit about modeling with splines. This is probably, Yardi's probably all over this, so splines can be a bit wiggly. If you are estimating splines, splines tend to wiggle, especially toward the edges, and then splines can be a little bit unpredictable when you get out in the tails. So as we do this, as we basically use splines to model the non-linear, just gonna say nonlinear risk, but what I mean is it's not linear in log space. I'm just gonna say nonlinear risk. It's helpful to use like a natural spline. So we have linear segments potentially in the tails when the data is sparse. And it's also helpful to add monotonicity restrictions. Otherwise, you fit a spline based on the available data, but off of the edge of the data, the spline can do random things. But if you impose monotonicity assumptions, then they can stabilize the fit. So that's an important part. So Yardi, do you use okay. Sorry. So I'll stop referencing. He told me he does a lot of splines. I was really excited. Okay. So modeling with splines, you want to stabilize them a little bit, have some linear segments. And the most interesting thing here is you can come up with a direct model for this exposure averaged risk. So what's a relative risk? The relative risk is you integrate along your risk from A to B, and then you normalize. That's your alternative group, because that's the vegetable, the high eating vegetable group. And then you divide by the integral of the risk from B0, that's your reference group, and you take the ratio of those. That's literally the model that you're using. So if you're modeling the relationship of if the relative risk is a spline, then the integral of a spline over a range, definite integral, is a linear function of spline coefficients. So linear is good, but when you divide the two, you have a ratio. If you take the log, you have the difference in logs, which is a nonlinear observation model. But that's like the right observation model. That's literally how the information is coming to you. So this becomes like a more competitive alternative than assuming that you can just associate all that risk to the midpoints, which is like the other methods are currently doing. So to sort of show what happens, there's a little bit of a plot. So we generate a truly nonlinear risk curve on the left, and then MR2 as the package that implements it basically gets that risk curve pretty much right. And then alternative methods that do nonlinear analysis struggle because they use the midpoint approximation rather than using integrals over exposure domains. The other thing is when we were first working on this, a lot of comments we got from the reviewers were like, why would you force the risk to be nonlinear? Which is like, it's like we give it the option to be nonlinear. And so if it's truly linear, the model will still recover linear risk. So that's why the left panel is here, is so you show that when the risk is linear, modeling it with a spline with some restrictions is still linear. And then you see there's like the effect of the stability is nice. There's more fanning out. But all the models, where they're covered by the data, all the models do pretty well, much the same, modular fanning out. But when it's not linear, it's good to not do the approximation, do the right nonlinear model. So that's the one thing I wanted to highlight. Okay. The second thing I wanted to highlight is outlier robustness, which is a really favorite topic of mine. So this is something actually, I was talking to Ken about. I was also on the call. So you might have some issues. If you're aggregating all the evidence, you might have some outlying results or some outlying studies. Why they're outliers, nobody knows. But if you include a study whose result is very far away, what that might do is it might change your mean effect, but it certainly might really inflate your estimate of between study heterogeneity. And since we really rely on estimates of between study heterogeneity, we want to hedge and make a method that's a little bit robust to that. So use this trimming idea, which is coming from Rousseau in 1984, called least trimmed squares. There are actually two methods. One was called least trimmed squares by Rousseau. The other one was called trimmed least squares by this guy at Cornell. And so my collaborator on the trimming paper, Dave McDavis, went to talk to him about least trimmed squares, but he didn't realize it was really trimmed least squares. And then Rousseau says in one of the papers, it's very important to know that least trimmed squares has nothing to do with trimmed least squares. So the idea of least trimmed squares is it's trying to solve the chicken and the egg problem. So it says, I'm going to have, let's imagine that we have our marginal likelihood for the linear case that I was showing you before. So you're trying to solve that, but at the same time, you're trying to identify what the outliers might be. So you're trying to minimize the best fittable, say 90% of the data. The best fittable 90% of the data, but you don't know what the best fittable 90% of the data are before you start. So trimmed least squares, you fit the whole thing, then you look at the residuals, then you pick, whatever weighted residuals, you pick the 90%, and that's how you decide. So it doesn't get around the chicken and egg problem. But least trimmed squares tries to solve these things at the same time. So least trimmed squares says, okay, to every data point, I'm going to associate a weight. That weight is going to be between 0 and 1. Okay, if it's 0, it's an outlier. If it's 1, I'm fitting it's an inline. And I'm forcing the weights to add up to 99. So if it's like I have 1,000 data points, I'm going to do 900 is the sum of those. So you have to invest your mass of 900. You have to spread it around. And so as you go, you put more zeros onto the stuff that's larger, which is less fittable. And you kind of do it at the same time. So it's a highly non-convex problem, but works supremely well in practice. And we really like it. It's like really straightforward. You say, I'm willing to fit 90% of my data to hedge against outliers, and that's it. And people ask if you can automatically detect the parameter that you actually should be trimming to, and maybe you can, but you have to really trust that every other aspect of the data and the variance is like completely precise, which turns out to be kind of crazy in practice. So we just by default do like a 90% inlier fit. And so here's an example. Like on the left is a stylized thing that I created. So here's a fitting a line through some data points. If I include 3 outliers near the top, it will raise the line up. And then if I do trimming, allowing that proportion of outliers, it will identify basically. And you can also vet, like you can look at it and you can see what was trimmed and you can kind of decide. So it's nice, it's straightforward. And then on the right, this is a real data example from vegetable consumptions in IHD. And they can see what data it trimmed on the way to fitting the spline relative risk. And then the trimming, it doesn't trim the points that are necessarily furthest away from the mean because they also report the variance. So the likelihood-based trimming accounts for so you can trim so if a point is like what I like to call I'll just skip that joke. But if there's a point that's like kind of close to the line, but very, very confident, overconfident, that can be trimmed because it's unlikely that it should be that close to the mean while that far from the mean while still having a very large confidence. So it's not the points that are always furthest, but here it is basically the points that are always furthest that are trimmed. And you can see basically the effect it has on the curve. Think of it as a hedge. Okay. So once we fit a spline to the data, we have basically a shape for the relative risk that we want to work with. From there on, we do something that's analogous to the linear slope random effect model. So we create a new nonlinear covariant, which we call signal, from this shape. And then we fit a linear mixed effects model, which uses that signal covariant. So, and we model the random effects as random slopes on that shape. So then you can see the effect. If this is the signal after we fit the linear model, the uncertainty relationship is that of a slope on that shape.
What was the rationale for doing it? So what is signal? Is a constant signal ij?
So signal ij is not constant. Signal ij is the data predicted for each ij. It's the predicted data from the spline.
Given what?
Given all the information. So this spline ignores grouping and gets a shape of the signal using the nonlinear model and all the incorporated variance information.
So it's just a prediction.
So it's just a prediction for that for each study. So then you get a prediction variable out, and then you use that prediction variable in place of a log, it's like analogous to the log linear risk. It's now a log linear model with respect to that shape. And then that accounts for the grouping, so it can modulate the effect size, and it can also obtain the uncertainty. So the uncertainty makes a lot of sense because for relative risk, the relative risk has to go, relative risk is relative. So it's pinched at zero always by definition. And so it makes sense basically to have a slope random effect while still accounting for the shape. So there might be other things to consider, but that was the approach we went with. Okay.
Then that interval you have there, then it's not a confidence interval, right?
This interval would be the one that I'm showing right now in dark. That would be a confidence interval for the predictions, the confidence interval for the predictions along the exposure.
And you're generating, how are you getting that confidence interval at each point? Using the signal.
It's just a linear mixed effects model with a covariate signal exposure. So it would be exactly the same as analogous to taking a log linear risk and plotting the uncertainty for the slope. Yeah. So you can definitely interpret it as a confidence interval for along the exposure axis. Yeah. Not the confidence interval for the beta itself, but when you push it through the prediction. Yeah. That's a good question. Okay. Great. So that's basically an important piece. And then the second piece that I haven't talked about yet is the basically assessing study quality. So this is kind of why the problem came to us in the first place. The nonlinear risk came about later as like it has to be done in order to work for dose-response relationships. But assessing study quality is a big deal here. So basically, there's many study designs that are possible, and there's typically best practices and gold standards. So randomized case control are best gold standard designs when they're available, but they're not available for all domains. And then you're looking at prospective cohort studies if randomized case controls are not available. So it's typically a notion of best practice along some version of study design. And then basically people worry about studies that deviate from any best practice, whether it's the design of the study, whether the study analysis accounted for confounders properly, and whether measurement was used with the best methods available. In each category, there's some potential deviations and worry about how to incorporate it. So there's many different community criteria that teach you how to read through your studies and basically try to flag any potential deviations from this, including the Cochrane collaboration, which has a chapter about it, the WCRF and grade criteria basically go through different potential levels where you say, okay, this is good, this is maybe questionable, this is not so good. So these are subjective criteria as identified by each framework, basically. So they're good at helping you figure out what might be going wrong, but it's important to try to incorporate that information so that you can test for it in the context of the model, basically. So the goal is to use the community identified issues and then code study level covariates, whether there's 0 in each category as a gold standard or 1 if they deviate from the gold standard, and then test in the context of the model as to whether they should be included to potentially modify the effect. Right. So this is basically exactly what I mentioned. So maybe let me not belabor. Yes. Yeah.
So these are all 0, 1.
So these are 0, 1. So if you look at each study in the study design, was it a gold standard or a suboptimal in that scientific domain? And then for the exposure assessment, was it self-reported or was it a nice, something a bit more systematic? For the outcome assessment, was it medical record or was it self-reported? And then not every domain is going to have this many candidate covariates because in order to have a hope of accounting for them, you have to have differences. You have to have the gold standard and studies that are not gold standard. You have to have enough data to be able to hope to differentiate. Yeah. Um, so, uh, right. So coming back to the previous place where we have a signal covariate, the signal covariate that we produce to understand the shape of the relative risk. There is a mean slope on that signal covariate. So if it's 1, it means that the grouping structure doesn't change the shape. But if it's not 1, it means the grouping structure can attenuate the shape a little bit. Then we have basically a possibility for the study level covariates to modify the slope on that signal covariate. And then we do a kind of a systematic pass using a lasso-driven variable selection tool. So lasso gives us an order of covariates to try, and we proceed to test each covariate, whether there's enough to support that covariate should modify the effect. And then there's a criteria for when you stop the process. And at that point, this piece is set, and some of those covariates are selected. So the research team can generate candidate covariates coded with 0, 1s, deviations, and criteria, assuming there's data available. If there's no data available, it cannot be tested. And then the lasso approach goes through and modifies it in this slope space to modify the signal. That makes sense. Great. So the important interpretation here is after we're done with this, we've explained as much heterogeneity, potential heterogeneity as we could have explained. So we worked really hard to incorporate this. So the only heterogeneity that we estimate now would be unexplained heterogeneity, presumably not due to the design from the candidates. So the remaining piece is understanding the unexplained between study heterogeneity. So basically, once we adjust the study signal, so it's missing an equation here. Let's go back to, yeah, I think this is good. So once we pick the covariates that we want to use to possibly modify the study signal, we want to estimate between study heterogeneity. Between study heterogeneity is fine, and then this is a linear mixed effects model. The issue is when studies are sparse, then it's very easy to underestimate between study heterogeneity and end up with having something like a 0 for the estimated between study heterogeneity. So what can happen is you have a well-studied area with many studies. You do a good job estimating between study heterogeneity, and then we'll see that's important to us. It sort of gets penalized in a certain sense by having that. You have a new emerging area, there's only 3 or 4 studies. You do the test, you get 0 for the between study heterogeneity. So basically we needed a solution to make sure that the approach, was robust to the sparsity of the studies. So we used the Fisher information matrix to assess basically as a proxy for assessing the variance of the between study heterogeneity estimate. So between study heterogeneity is variance. So the variance parameter, the variance of the variance is very hard to assess when the variance parameter itself is hard to assess. So it sounds like a reach. However, use the Fisher information matrix, it does not depend on the estimate that you're actually getting. It's very weakly dependent on it. So basically you have the data you've currently collected. You have the design matrix that gives you a way to get at the potential variation in between study heterogeneity. So what we call the effective between study heterogeneity is the point estimate that we get plus a quantile coming from the Fisher information matrix. Then we did some simulation studies that are kind of shown here that can help alleviate underestimates of between study heterogeneity, but this is certainly a decision that the burden of proof study makes. Okay. How am I doing on time? I don't want to run out before I show you guys the plots. So yeah, we're actually here. We're at the finish line. So final thing is this philosophical distinction that we talked about. Okay, so if you look at the plot above is showing exactly the confidence interval for the vegetable case. If you keep doing studies on vegetables, even if the results are as varied, the confidence interval will continue to shrink just because it's a population mean. So this motivates having an alternative measure that basically captures not only the, some theoretical population level, but also how varied the estimates actually are. So the question that we want to answer is, if we do a new criterion study, like a huge gold standard study in Seattle on vegetable consumption, how varied might those results be? So we produce a confidence interval that's classic. In addition to that, we also add the estimated effective between study heterogeneity directly onto the mean effect, which is shown, I don't know if you guys can see, it's shown in a little bit of a lighter color. So the interpretation for the outer uncertainty interval is this prediction interval at the study level, not at the individual level and not due to any design factors, but like if we were to do this study in Seattle, how varied might those results be?
I mean, so the top one is essentially, it's a point, point-wise, those are point-wise confidence.
Yes.
Correct.
Point-wise, the top one shows you point-wise confidence intervals along exposure. And the bottom one shows you that plus something else. And the something else is answering this question. And so what we've basically done in order on our way to summarize these things is that we've created a conservative estimate. We have the mean estimate, and in addition to that, we have what we call the burden of proof risk function. So we take the 95th percent quantile that's closest to the null and report that in addition to the mean risk. So the interpretation of this is, given all the data, and I'm explaining between study heterogeneity, we are confident that the risk is past this point. So that's like an additional measure that we report with each study, and it collects into it all of this other information, including the classic confidence interval and this like arduously derived estimate of between study heterogeneity. And then we summarize it for every domain by averaging the value across 15th to 85th percent exposure in the data we're studying to come up with one number. So we provide all of this in the publications.
Then what does that number tell you if they're actually interested in dose response?
So that number is only to give, so it's pretty hard to compare dose response relationships. So the full picture, so the full picture gives you all the information about the dose response relationship, including the mean estimate, the classic uncertainty interval, and the uncertainty interval that includes between study heterogeneity at the study level. So that's the full picture. And then there's just a progressive set of summaries that we also provide. So the summary that we provide that lets us compare these to each other is this burden of proof estimate and its average value.
So like when you say compare things to each other, like compare eating vegetables to some completely different risks?
Yes. So this is basically, let me finish this, see what you think about this. So we can do exactly that. So we can give a star rating to the overall evidence for a particular domain of science. So we can compare eating vegetables versus heart disease to eating red meat versus heart disease. we can summarize it with a number and a star, and then you can look and see the entire risk outcome relationship. So basically, the way you get from the burden of proof risk function to the stars, so you take the quantile, we average that across the exposure, that gives us a score, and then there's always some there's essentially an arbitrary decision that's explained in terms of levels for harmful risk, in terms of how that number is then delegated to stars. So smoking versus lung cancer would be a 5-star risk. I will show you that because even though there's a lot of between study heterogeneity, the lower quantile is definitely high. And then we could look at some of the other ones that you're interested in, like red meat versus heart disease. So at the very simple level, you can discuss stars. And then if you get into it, you can see the entire set of evidence for every domain.
What did you decide on eggs?
Eggs, we don't have eggs in the global burden of that. I wish I think that's why I took it out, because every time I gave the talk, actually, it's a really fun talk to give because people come up and say really interesting things afterwards. So in applied math, and Greenbaum just came up and said, so what's the egg? Should I eat eggs or not? And then I didn't know. So I felt bad. So I took the example out. And then another talk, somebody came up and told me, my wife tells me not to eat meat, and then just left. So it's always that people have strong opinions on these things. So let me see that. Let me maybe show you some examples that you guys might be interested in, and then go back and finish the talk a little bit. So if you go to burden of proof viz, this is an interactive visual tool that the visualization team makes. So here, these are ranked. I hope you guys can kind of see. These are ranked by stars, and they're kind of ranked in decreasing order of that aggregate signed quantile risk score. So then, does anybody have? So there's 177 of them, and there's some filters. So maybe let me show you which one do you guys want to start with.
Numbers.
So the numbers in the green bars is the exposure average value of the burden of proof risk function in log space. So a higher number would correspond to some measure of average excess risk across exposure as the star. Excess risk. Yeah. But this is not directly, the number is not directly interpretable.
Okay.
So the number, that's actually a really good point that you're implicitly making. But
I was trying to find out if the number was.
the number is not directly interpretable. The number is not directly interpretable, but you can compute excess risk from that number, but it would be averaged over the study interval of exposure. So for example, if you wanted to understand this 0.86, you can do exponential of 0.86 minus 1, and that would be the average risk across the studied exposure for that study.
15 to 85th percentile.
Right. 15th, 35th percentile. We do. So this is, yeah. So let's pick something. So let's do risk is maybe diet high in red meat. And let's do red meat versus ischemic heart disease, because this is one that people often care a lot about. So this has a risk outcome score of 0. So this doesn't have the red line, unfortunately, yet, but we'll have the red line in the future. The risk outcome score is 0.01. So it's a 2-star risk by that classification. But if you look between 15th and 85th percentile, you draw the red line, it's close to the null. So that's why, the excess risk in the conservative estimate is low. And then this is kind of the risk outcome pair. And this gives you the full set of data that we have. You can sort of close your eyes to the curve as well. If you click on the data points, you can see which studies they came from. And then you can also see what are the other data points coming from those studies. If you highlight them, they'll show you where the alternate exposure is and how it maps to the reference exposure. Yeah.
Difference in study times that you're following people?
So time is not accounted for. Variables like time or age are not accounted for in the model, but it's possible that the research team did adjustments, not necessarily in time, but for example, in age. So there may have been an adjustment that was done in order to analyze all the data in a comparative way, but in terms of the analysis that I've shown you, it's exactly like this. So there's no additional variable for those things currently. Yeah, it's a great question. Yeah, so if you,
To risk of the outcome ever.
yeah, risk of the outcome ever. I don't think time is typically a thing. So if it changed, this wouldn't necessarily catch it unless you did some adjustment. Putting in additional axes of variation is difficult. Yeah, just probably, yeah.
But this, you have the studies and then the study level covariate that you have are those ones related to policy. Like
Yes,
ones from-
only binary. That's right. That's right. That's right. Great. Does anybody else have, because they're very quiet on what actually to look at. Does anybody want to look at any particular, coffee is not in here. What? There's, well, let's just look at the filters. Risk is, so there's diet, low in various things. There's systolic blood pressure, the kidney dysfunction, secondhand smoke,
Alcohol use. Better.
yes. Where is that one? What's it?
I'm writing for drugs.
High alcohol use. So let's look at high alcohol use and other pharynx cancer. This one, let me change it to log space. Yeah, so there's not very much here. So it's actually a great example. So it looks like there's very little data on this, but it's showing a high risk. And so you can see this extra bit is penalizing you for the lack of other studies, basically, but it's still the risk reported is so high that this is completely data driven. So if there's, if the data changes, the results change as well. That's
You have alcohol use in breast cancer? Right.
I think so. Yes. 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 Yeah. So yeah, so this is so there's a lot of heterogeneity in the beginning part of the curve for breast cancer. Okay. Yes.
I have a question on the previous plot. If I remember correctly, like there were only like 3 or 4 studies.
Yes.
Plot. Like, is that in cases like that, is there a reason why you would want to extrapolate up to like high alcohol use of like 400,
It's
140 per
it's-
day? Like, why not
it's
just
an
cut it off?
incredibly good question. So we typically, the visualization tool shows what the studies themselves reported, but your confidence for few studies going out to 400 grams per day should, you should take that with a grain of salt, right? So this is the exposure is, exposure is controlled by some of the data that's reported. For alcohol, you have, I come from Russia, so maybe it makes sense, but for alcohol, you have some very high levels of alcohol exposure. Great. So let me just wrap up a little bit and we'll see if there's any additional questions here. So I have this visualization dashboard, so you can always take a look and then let us know if you have any questions or suggestions. And then there's been several of these studies that have been published. There's a methods paper in JCGS that we wrote on handling non-log linear relative risk correctly and using trimming. And then there's a methods paper basically explaining these many steps that you guys have been very patient with me in the burden of proof study. And then there's a reply to some researchers who raised concerns, which maybe addresses a little bit more clearly this prediction interval at the study level question, because it's easy to misunderstand what the role of the outer uncertainty is. So that hopefully puts it to rest. And lots of scientific teams-led work using this to analyze the 177 risk outcome pairs we have currently in the tool. And then there's a lot of code that went into this. So in terms of basically there's an entire stat which was written and improved on by Peng Zheng, who's the lead author on many of these things. So X-spline for Yardi is a really nice it's a really nice package that lets you incorporate
Very careful next time.
let's say incorporate definite integrals of spline coefficients as an observation measure. That's not super easy to do. Line 3 is a trimmed linear mixed effects models that combines trimming and linear mixed effects. You can use it for different things. Mr. Tool and Mr. Burt, there's like a suite of packages that handles basically all the wrapping for the different mixed effects models with spline ensembles. And then BopForge is also an open source code that codifies all of these steps so that collaborators who are not at IHME are now able to run these BOP analyses by basically following the steps. So this is like all open source. You guys can also take a look. And yeah, we're currently working with Nora to extend to categorical risk analysis, which has some wrinkles, and then higher dimensional risks are of interest. And you already asked about time, but there's lots of examples. So, for example, birth weight and gestational age are two axes of exposure that affect infant mortality. And then a lot of questions come up when you start worrying about higher dimensions. So I think I'm going to actually stop here and I can take questions, possibly looking again at the Viz tool if you guys want. But thanks very much for your attention.
Questions?
Question going back to like slide 13, maybe.
Uh-huh.
And it's more just like a philosophical question where we're like trimming
Yes.
observations. I think there's like pros and cons. Like I have no weight in the game. So
Yeah.
just genuinely curious. Some people view outliers as the signal you might pursue, and other people view them as a distraction from the signal. So I wanted to hear like your rationale in this setting for trimming.
Yeah, I think that's a really great question. Trimming, there is definitely different views of it. For us, we've placed so much emphasis on getting that between study heterogeneity. So if we estimate a very large between study heterogeneity for a certain domain, what that would do is that might give it a lower score and a lower star rating, which is like a summary measure. And so if there is a particular study that's far away from the rest, maybe that's worth figuring out why it's that far from the rest, but it will essentially, that one thing can have an undue influence on the gamma. So I think philosophically, we want to be able to hedge against that happening. But the more you trim, the smaller your estimates of between study heterogeneity are going to be. So there's this like delicate balance with between study heterogeneity because there's a higher level effect that you're getting. So we go really hard to make sure that we can estimate something, even the variance of it, when we have too few studies. But we don't want a single study to just completely smear out, our estimates. So there's definitely a decision there, and the 90% level of trimming has been just wildly popular across as a way of like a moving everybody forward in a cohesive way. But you always have the option to see what was trimmed and thinking really hard about it and coming back to see like, do we want to be trimming this or why is this different and things like that. It provides at least a transparent result. Yeah.
That just prompted a follow-up question. So you always have the option of, and this is one of the things that I wonder about when I learn about different review methodologies.
Yeah.
Do you guys come back and check everything that's trimmed? Or are these choices made so that you don't have to? Does that make sense?
Yes, the question is, do we come back and check or the choice is made that we don't have to? Typically what happens in the review process, people want to see sensitivity analyses. So they'll want to see if there's an effect on trimming and what it is, and if it completely changes the results, that causes a kerfuffle. So there's a checking in that case. I tried initially because I was, again, sort of coming in, I was really interested to try and follow through. It's very hard when you go and look to then say something sensical about why a result from a particular study might be different. So in terms of why something was trimmed, that's a harder question. But in terms of sensitivity analysis, that's a very classic thing to check. So it's not that these results are, yeah. Great. Yeah.
Question also on least trim squares. Your slide mentioned that it's not convex.
Yes.
Just curious on how you actually optimize it.
Yes, thank you. Oh my gosh. Oh, thank you so much. Okay, so you can optimize it. It's a particularly nice thing you can do. So this part of the objective is smooth in beta. And then to every term, you associate a weight, and then the weights live in a convex set that's easy to project onto. So one thing that you can do, the basic algorithm is in Palm. It's called proximal alternating linearized minimization. Is you can take gradient descent with respect to beta, like with respect to your spline coefficients, that gives you a step. And then you do a prox gradient descent step with respect to W. So the derivatives with respect to the weights are literally the function values. And then you project that thing. Kevin was asking me about the prox. Kevin,
What?
prox. Prox is right there. You do prox on the projection onto the cap simplex and you alternate. That works pretty well. When we were working with Dave McDavis on this, did a similar thing in like a larger machine learning setting where we needed to variance reduction, this and that. And then in terms of what we actually do is we actually partially minimize in the code. We partially minimize with respect to beta. So for fixed weights, we go pretty far in the beta and then we do a prox gradient step. So we have outer trimming iterations because there's not such a need to alternate so much.
Yes, is it like guaranteed to attain a global minimum, or is it just?
Definitely not. So it's just
Okay.
like for non-convex, you have a really hard time guaranteeing anything. The nice thing is you can vet what was trimmed. So there's some vetting plots that also have been shown. We'll do a modified funnel plot, and you want to check that the things that are trimmed are kind of on the outside of the funnel that you got. And you can check the stability with respect to data. So you can validate it, but you can never guarantee that it's a global minimum. But for being that, it actually works. It's everybody's favorite now, like at least at IHM, it's everybody's favorite method of statistical robustness because you just say, I'm going to fit, 90, 95% of the data. It does its thing, and then you can see what it did afterwards. Yeah, I have a lot of thoughts on convexity and non-convexity, but yeah, let me stop.
Cool.
Yes.
Have you had any thoughts or incorporated into your visualization at all? The fact that a lot of these outcomes that you're comparing are really competing risks with each other?
Yes, the competing nature of the risks is accounted for in other streams that we didn't talk about further down in the GBD. So definitely we're not prepared to speak coherently exactly how, but there's a lot of work on exactly that topic afterwards. So each risk is supposed to be controlling for other related things. So each risk analysis is supposed to have accounted for it. But then once you have them, then there's the fact that they combine. So that in the understanding the burden to how much the risks contribute to the burden, there's that piece. Yeah. So the GBD itself is large. This piece actually, for people new to the GBD, this piece is one of the most self-contained in the sense that the inputs are just the study results and then this methodology that I described. So there's no additional processing or covariates outside of what the teams might do to prepare the data for the analysis. So this is actually such a lucky starting point for us, is coming into a very standalone thing so we could do work without understanding the GBD. But the GBD itself is a large enterprise, so there's many pieces where the one you're worried about is definitely part of it. Yeah.
How do you feel about combining effect size and uncertainty in one metric in some sense? That feels like that's what you're doing with your star thing, right?
Yes.
It feels like they sort of have orthogonal information in some sense, and that's how we treat them typically. I mean, p-value that gives a sense of the certainty, and then you have effect size and a bit of efficiency. So why would you combine them? How do you feel about it?
I think I really like it basically. So the idea is it's answering. So it combines two things. It's definitely a decision. Originally, when we were thinking about this wasn't the way we were trying to assess the strength, but then it turned out to be like a really natural way to assess the strength. If you take into account the uncertainty, that can get you like a lower bound type thing, right? And for summarizing, the lower bound has been particularly intuitive because you can have a risk with a very high log relative risk, but it can have huge uncertainty. And then you can have a more mediated one, but it can have lower uncertainty. And those two things can come up with the same quantile, right? Because the bigger one has bigger uncertainty, the smaller one has smaller uncertainty. But fundamentally, the reason why it makes sense to give them the same value is we're about equally sure based on the data that it's higher than that bound for each. The excess risk is higher than that bound. So it's actually works together very well because otherwise you can get distracted by how high the mean risk is without taking into account the fact that maybe it hasn't been super well studied or the data for it is quite noisy. So is it a complementary measure? That's what I keep emphasizing. We have that in addition, but for us, it's been working well to compare these domains to each other. It's not the only choice, but it's a good choice. Yeah.
How many people do you guys have?
So IHME, so I don't completely know, maybe 500 to 600, but they're not all working on this. They work on many different areas. So this has a lot of teams contributing. Yeah.
All right, let's thank our speaker one more time. Just a quick announcement. So next week, our seminar is on Zoom, and then in 2 weeks, we have our exciting student seminar. So stay tuned for the next 2 weeks. Thank you all.